Good afternoon, everyone, and welcome to Year 11 Physics. In today's lesson, we are going to be looking at conservation of momentum. In recent lessons, we have looked at what momentum is, and we have said that momentum is the tendency of a body to maintain its motion. We've looked at this idea of impulse. We've defined impulse as what you get when you apply a force to a body for a period of time. We've also defined impulse as the change in momentum that a body experiences when you apply a force to that body for a period of time. So in recent lessons, I've been talking about momentum and impulse, and I had the good fortune of recording some of those lessons. If you weren't present or if you wanted to look at them again, you can find them on sector, change in momentum and impulse. Momentum and conservation of momentum. These two recordings here are recordings from last year, and they were okay. They're a little bit back to front, but they do cover some useful ideas. I encourage you to look at those. So yeah, go through, have a look at those. Have a look at those videos. They've been recorded, put up there. I think this one here, lesson 31, is the video from this year. And I think when we look at these two videos in this section here, they're the lessons that I recorded from last year. Have a look at them. They're between 10 and 20 minutes each. Watch them on fast forward. They may be of value. So today we want to talk about the conservation law of momentum. Momentum is conserved in any system, whereas a system is that thing that you are studying. In previous lessons, we've mucked around with trolleys, throwing trolleys against each other, seeing what they do. The thing that you are studying is that environment where you're focusing your attention and the bodies that are moving in that environment. As we go to look at conservation of momentum, we look at the simplified version where there are two bodies in the environment moving relative to each other. So either both of them moving, one of them's moving. They tend to be moving in one dimension only, forwards and backwards along a line, just to keep it really simple for us. And we talk about how the momentum of those bodies is constant throughout the time that we study that system. So if we're studying the system, there's two bodies, maybe one of them is moving towards the other, where the first body is moving, the second body is stationary. Well, the momentum of that system, as we observe it, there's momentum because one of the bodies is moving. The momentum stays the same no matter what time we look at the system. At a later point in time when we look at the system, it might be that both of the bodies are moving. Well, the momentum when there was only one is equal to the total of the momentum of both bodies moving. Or it may be that the other body's moving and one has become stationary. So momentum is conserved. This is one of our cardinal rules. Energy is conserved, momentum is conserved. This is one of our very important rules. Momentum's conservation comes out of Newton's third law of motion, or rather, we can derive the conservation law of momentum from Newton's third law. If you look at this slide here, we've summarized Newton's third law of motion with the equation F equals negative F. So you'll notice I've got the subscripts there, F1 and F2. So if there are two bodies playing a force against each other, two sumo wrestlers pushing against each other, then the force of body one acting on body two is equal to the force of body two acting on body one, just in opposite directions. Just in opposite directions. Now we define force as mass times acceleration. So the force on body one is equal to the opposite of the force on body two. When we look at that, force one, we have the mass of body one, the acceleration of body one. Well, that's equal to the opposite of the mass of body two, the acceleration of body two. We take that a step further. We look at our definition for acceleration. Our definition for acceleration is the change in velocity per unit time. V minus u on t. So our body one, there's the mass of it, then we look at its final velocity, its initial velocity. So final velocity subtract initial velocity and the time that it took for this to occur. That is equal to the opposite of the same quantity for body two, m2 v2 minus u2 on t. Now, you'll notice I've got these subscripts for one and these subscripts for two. So there's m of body one, there's v of body one, there's u of body one. There's m of body two, there's v of body two, there's u of body two. There is no subscript for t, for time, because the time experienced for these bodies as an interaction occurs between them is identical. So we don't need to see T1 or T2. The time for body 1 is the time for body 2. So the T has no subscript. The T can be cancelled out, and it leaves us with M1V1 minus M1U1. That's our change in momentum of body 1. And that equals the negative of M2V2, body 2, minus M2U2, body 2, the change in momentum of body 2. You'll notice throughout this series of equations, I've got white and green text. So for the sake of this derivation, I've got white being all the letters that relate to body 1 and green being all the letters that relate to body 2. Can't see that in the screen? You'll see it in the OneNote when you see it. I mean in the PowerPoint. So we take this down and we see we've got the change in momentum for body 1, M1V1 subtract M1U1. That's change in momentum for body 1. That is equal to negative, indicating opposite of the change in momentum for body 2. Now, what does that mean? Opposite of it. Momentum is a vector property. It has direction. So when you see that little negative sign, and allowing for the fact that our current study in year 11 focused on two bodies acting in one dimension only, the negative indicates opposite direction. So the change in momentum for body 1 is a vector. It has a quantity and a direction. The change in momentum for body 2 is a vector. It has the same quantity, but the opposite direction. We rearrange and reshuffle so that all the initial momentums are on the left and all the final momentums are on the right. And we find that we have, after having multiplied out the negative, we have M1U1 plus M2U2. So all the initial momentums on the left equal all the final momentums on the right. And this tells us, therefore, that the sum of all the initial momentums is equal to the sum of all the final momentums for any interaction between these two bodies. Could be 3 bodies, could be 4 bodies, could be 20 bodies acting in 3-dimensional space. If you're playing one of those massive online space opera type battles, you get all your spaceships heading in towards each other, 200 spaceships in various different orientations, moving in 3D space, all towards one big final collision. The momentum of all the spaceships before will be equal to the momentum of all the spaceships after. Conservation law of momentum. Here's a sample problem. A girl with a mass of 50 kilograms running at 5 meters per second jumps onto a 4 kilogram skateboard traveling the same direction at 1 meter per second. So try to imagine that situation. She's running pretty quick. She's got her skateboard in her hand. She does that thing that skaties do where she kind of throws it out in front of her. Have you guys seen that? Yeah. Okay. And then she runs a bit faster. So she goes to catch up to the board. She jumps. She lands on the moving board. She lands on the board. She's got 5 meters a second. The board is moving with 1 meter a second. They are then one thing. The two of them are one thing. The girl and the board become one thing. The sum of the initial momentums is equal to the sum of the final momentum. So let's look at that. What are the initial momentums? There's the momentum of the girl. There's the momentum of the skateboard. What are the final momentums? There is the momentum of the girl and skateboard. One body. Now they are one. So we say MGUG plus MSUS, the girl and skateboard, equals MGVG plus MSVS. But because they're one body, that V for the girl and V for the skateboard, it's actually the same thing. So you can now take the V out of it and you end up with mass of the girl plus mass of the skateboard in brackets multiplied by their common velocity because they're now one object. Then you can find the common velocity of the girl and skateboard together and do that with a bit of algebra, plug in your values, and you end up with 4.7 meters per second. And that kind of makes sense because the girl was moving at 5 meters a second. The skateboard was moving at 1 meter a second. And so their final velocity is somewhere in between those two values. It's a little bit closer to the girl's initial velocity because the girl was a much greater mass than the skateboard to start with. Okay, Gadget's asked another question. This one is relating to conservation of momentum. A railway wagon of mass 2.5 tonnes moving along a horizontal track at 2 metres per second runs into a stationary engine and is coupled to it. After the collision, the engine and wagon move off together at a slow 0.3 metres per second. What is the mass of the engine alone? Give your answer to 3 significant figures. So I suggest that we draw a free body diagram, or we draw a diagram to indicate what's going on. So this is a conservation of momentum question. The momentum of the wagon before is equal to the momentum of the wagon and the engine after. I don't include the engine initially because it's got an initial velocity of 0 metres per second. The wagon before, 2,500 kilograms, they said 2.5 tonnes. 1 tonne is 1,000 kilograms. Moving at 2 metres per second. So, conservation of momentum, we build ourselves an equation. I've got down here M1U1, M2U2, so M1 being the mass of the wagon, M2 being the mass of the engine. Initial velocity of the wagon was, we said, 2 metres a second. The initial velocity of the engine is 0, so that does actually cancel that entire expression out. We've got mass plus mass multiplied by V. The final velocity on this 0.3 metres per second. And that's our mass of the engine. Some of the initial velocity, some of the initial momentums, some of the final momentums, just following it through, and that's what we get. Okay, Gadgets asked me to look at this question. A marathon runner with a mass of 70 kilograms is running with a velocity of 4 metres a second north and then turns a corner to start running at 3.6 metres per second west. Calculate the marathon runner's change in momentum. So here we see we've set up the question. We've got north, south, east and west. We've got our initial momentum, we're going north. Our final momentum, we are going west. When we look at that, our change in momentum is going to equal momentum final. Our change in momentum is going to equal momentum final subtract momentum initial. But with vectors, we don't like to, or with these types of things, we don't like to, graphical analysis, we don't like to subtract vectors. So what we're going to do is we're going to add their opposites. So instead of subtracting the initial vector, we're going to say PF plus the final vector. So we'll go look at that one now. All right, so looking at this one here, we're going to find our change in momentum, final momentum, subtract initial momentum. We would rather say, since we're doing a graphical analysis, we're working in 2 dimensions here, it's final momentum plus the opposite of the initial momentum. So we've got our final momentum, that has not changed, but our initial momentum, we've got the opposite of it. Now we're going to find the change in momentum, that's this one here. This is delta rho. So delta rho equals that one there. Now we need some numbers. So we've gone and had a look and found our change in momentum using Pythagoras' theorem. The square of the hypotenuse is equal to the sum of the square of the other two sides. We've got the square of this negative pi. Well, of course, that's just going to be the same as the square of the positive pi. So end up with 252 squared and 280 squared. That gives us 141,904 squared, which means the change in momentum magnitude is 376.7 kilograms meters per second. But then we need to know the direction of the change in the momentum, and we'll need to find this angle here, theta, and we could use tan to find that. Okay, so we try to find the direction. We find the direction from the activity. We know that the change in momentum is this green vector here, where this is north, south, east and west. So that's north, south, east and west. So we've gone south and come up this angle. Now that angle there, theta, is 48 degrees. So the angle here, if we've got north, south, this angle here, we'll call it phi, is 90 degrees subtract theta. And so that ends up being 42 degrees west. So the question asked by the student is, how do you figure out the answer here with the direction? What I've done is I've taken my vector diagrams, so we've got the sum of the two vectors. We don't want that, we want the difference in the two vectors. So we got the final momentum subtract the initial momentum here, where the final momentum add the opposite of the initial momentum, so it's south. We go through, we get the magnitude down here, but now what we want to know is the direction of the vector. This is a right angle triangle, so I can use theta and I can use a bit of trig. Tan theta equals opposite over adjacent, and that'll give me the angle theta is equal to 48 degrees. I then use my compass rose. Okay, my compass up here, so we've got north, south, east, and west. There's my vector. This is theta. I want to know south, how many degrees west? So theta is equal to 48 degrees. So it's south 42 degrees west. South 42 degrees west.